Welcome back to ECE 501B. You do have an assignment due tomorrow, which is deliverable number 1. It's not that elaborate. I just want you to communicate to me that indeed you've thought something about your project and this is what you're planning to do. That doesn't have to be a 20-page document. That can be a sentence or two or a few lines to communicate that to me. Homework number 7 is due, wow, I guess it's due in a little bit of time. I'll try to post homework number 8 shortly. And homework 8 and the final project deliverable, which includes 2 different deliverables, that's due on the last day of class. And as a reminder, our final exam is on a Tuesday, and that's not quite a week after the last day of class. It's 6 days beyond our last day of class, and it's a little bit later in the day. It's from 6 to 8 p.m. Today what I want to do is start by reminding us of where we're at, and that is to really be decomposing these operators as if they were complex numbers, or that's the analogy. A complex number has a magnitude and an angle, and that's really how I want you to be thinking in the simplest terms about these operators. A complex number in polar form has a magnitude and an angle. Now we're going to be thinking of an operator in that same way. It has a scaling property, so it can now have a magnitude, and it has directional properties, so it has an angle. And we are now thinking of those as the positive operator piece of an operator, and then the isometry part, or the rotational piece. And that's what I'm hoping we start to pick up from today's class. And we'll talk about what that looks like eigenvalue-wise relative to an isometry. If it's simply rotating, you can think of it like you're being on the unit circle in the complex plane. Now you're not changing the scaling at all. You have a magnitude of 1, but now you might have an angle. And that's now the unit circle in the complex plane is one way to simplify down this isometry, which is saying that our eigenvalues of that isometry have a magnitude of 1. Question? So I'm not quite sure what you're meaning by so now the positive operator, in terms of a one directional, you'll be thinking about the eigenvalues of this positive operator, and they now are expanding or collapsing relative to if, and a positive operator could have a scaling of 1. But now is it contracting or expanding in a given direction? So if you think of a positive operator having some orthonormal basis that will diagonalize it, now you're able to just concentrate or focus on the diagonal entries, and those are these non-negative numbers, which are the eigenvalues. And those are going to be non-negative, and they either contract or expand in that particular direction. The isometry now allows us to rotate from that, and that motivates this polar decomposition, which is, like I said, the generalized form or a generalization of the polar form of complex numbers. And that then says that we will have this positive piece, so we're factoring a linear operator t into 2 pieces. A positive piece, which is the positive square root of t dagger t, and a rotation piece, which is this isometry. And we're going to then decompose a operator into these 2 parts, and that gives us another way of thinking about these linear operators as far as what are they doing. They're expanding and contracting and rotating. And they can do that together. They can dance cleanly together. And an extension on that will be singular values, and maybe you've heard of singular values. I don't know if we talked about singular values in this class yet, but that's another way of thinking about how you're scaling the information that you're processing via these operators. You can now do a singular value decomposition, and a piece of that singular value decomposition are these singular values, which are not, well, they're not eigenvalues, but they actually are equal to eigenvalues of the positive part of our decomposed linear operator. So if we take the eigenvalues of the positive square root of t dagger t, those in fact are the singular values. And these singular values are non-negative numbers. They don't have a negative sign to them. Singular values are always going to be non-negative. We'll get into an example of singular values. Then we will go through the entire decomposition of singular value decomposition, which now is dealing with two different orthonormal basis sets, the singular values, and that combination now produces a linear map. And now it can actually be a linear map and not just restricted to a linear operator. And what's the difference between a map and an operator? Or why am I making that distinction? So an operator is square. It may or may not be invertible, right? An operator is just mapping from one vector space back to itself. So the input vector space dimension is the same as the output vector space dimension. A map can have different input vector space dimension and output vector space dimension, and we usually don't have a clean thought process of an inverse in this inconsistent dimensions, but you can have a generalized inverse, and the singular value decomposition will allow us to be talking a little bit about that in terms of constructing a lot of different numerical schemes, and a lot of nice numerical schemes are based on the singular value decomposition, which is how I spent my master's degree, used that as a numerical number cruncher to perform different operations. But I was extracting from the singular value decomposition these orthonormal vectors. And that identified the four fundamental subspaces. Do you remember what those are? Where can we get to from a linear map? The range, that's what we can touch. What is sort of hidden from us with a linear map? The null space, so all of these vectors of that linear map that get mapped into the zero vector are in the null space of that linear map, and then we have the orthogonal complements of those two pieces. We have the orthogonal complement of the range, because the range space could be dimensionally different than the null space, since we're not dealing with an operator necessarily. The dimensions might be different. And we have the orthogonal complement of the null space. Those are our four subspaces of a linear map. Range space, null space, maybe it's funner to say the perp. The perp, the perpendicular component, or the orthogonal component of the range space, so the orthogonal complement of the range space and the orthogonal complement of the null space. I digress. Let's move on. Let's go back and recap. Before we get to singular value decomposition, let's just show that we can decompose a linear operator in terms of a scaling and a rotation. That's the more basic piece, and then after that we'll step into the singular value decomposition. But now we'll just talk about polar decomposition, which involves these two pieces, positive operators and isometries. And a positive operator, definition-wise, has two parts. One, it's self-adjoint, which means we have the operator itself is the same as its adjoint. And what's the adjoint do for us? In general, if somebody said, oh, we're talking adjoints today, what's one way that you could start thinking about that? So now we're just talking about being able to move this linear operation from one slot in an inner product to another, from the first slot to the second. That's the adjoint. If it's self-adjoint, that map or operator stays the same in the first slot and the second slot. So it's self-adjoint, and we have this non-negative behavior of the inner product for that linear map, if it's positive, that linear operator. Isometries, on the other hand, are the rotation or direction piece of our decomposition. And here, what is the major part of an isometry is it preserves the norm. If you give me a vector and find its norm, then with respect to that same norm, if I operate on that vector with an isometry, I'm not going to change the value, that scalar coming out of the isometry applied to that vector. So SV's norm is equivalent to V's norm for all V. And that says then that S is what? I'll give it away. There's the answer. And this I said verbally last time, I didn't write it down, but now I've written it down. If the norm of SV is equal to the norm of V for all V, then if V is non-zero, we know that SV has to be non-zero also, which means that we can't find a vector such that the SV maps us to the zero vector. If we could, then this wouldn't be true, would it? We could find a non-trivial vector V if S had a null space that could give us a norm of 0, but the V that we started with, if it's non-zero, will not have a trivial norm. It will have a non-zero norm. But because of that, then, we can say that S doesn't have a non-trivial null space. It's injective. If S is an isometry, then S is injective because SV equal to 0 can only be true when V is equal to 0. And that's the trivial null space if we have SV equal to V. And for operators instead of maps, for operators, if it's injective, then we have these three equivalences. If it's injective, it's surjective and invertible. Surjective meaning has an R in it. So now the range space fills up the entire output vector space. Injective has an N. It's dealing with the null space. It's saying now we have a trivial null space if it's injective, which means the only vector that produces the 0 vector when we map it through our map S, in this case, would be the 0 vector itself. So every isometry can be inverted. We can find the inverse of an isometry. That's not necessarily the case for a positive operator, because positive, remember, is a little bit mislabeled. It really should be non-negative operators, but the positive name has just stuck. We could have eigenvalues that are 0. And so if we take this orthonormal basis and map this positive operator into a diagonal, some of those diagonal entries could be 0, and we would still have a positive operator. But then would that operator be invertible? No. Anytime we have a 0 eigenvalue, we can't invert that operator. Now we can actually come up with a bunch of equivalent statements relative to isometries, and that's in the form of the following theorem. Theorem 42 is the following. Given that we have an isometry, so these are characteristics of isometries, given S being a linear operator on a vector space V, the following statements are equivalent. A is that linear operator S is an isometry. Now if you have an operator that's an isometry, these subsequent statements are equivalent. So if you have an isometry, you also have any of these other statements. The next statement B that's given says that the inner product of SU with SV is the same as the inner product of U with V. And that's true for all vectors U and V in our vector space V. Or you could say if I have an isometry, it preserves the inner product. That's one way of thinking of that. But now that you have this relationship, that allows other statements to sort of fall out. One such statement is now if I have S applied to E1, S applied to E sub 2, S applied to E sub n, that set of vectors is orthonormal whenever the first set of E's, E1, E2 through E sub n, is orthonormal. And that one, hopefully, you can sort of just see falling out from statement B. You know what happens when you take the inner product of any of these E's with each other. They're going to, if the subscripts are different, you have a zero inner product. If they're the same, what's the value of the inner product? If the subscripts are the same, inner product of E1 with E1, 1. Now we have a new set of vectors, SE1, SE2, up through SEN. Well, if we plug it into B, those immediately become just like this other set, E1 through E sub n, and that set was orthonormal. So we now know that SE1 through SE sub n is orthonormal by statement B, since it preserves inner products. Statement D, there exists an orthonormal basis E1, E2 up to E sub n such that SE1, SE2, SE sub n is also orthonormal. E is if we take this isometry S and find its adjoint and apply that adjoint operation to the operator itself, that's equivalent to the identity map. Then we have F, which says that S applied to the adjoint is also the identity map. G, the adjoint of that isometry is an isometry. and H, S is invertible, and the inverse of S is actually, if you just look at E and F, it's going to be the adjoint of S. We're not going to chase our tail today because that would be quite long, right? A through H, and then H to A. So I'll just refer you to the book, but we've already sort of talked a little bit about how you can justify or explain away some of the equivalence behavior of these statements as we were writing them down. Let's, instead of proving, maybe write or rephrase these, maybe in the form of a summary. If we're dealing with isometries, if this operator S is an isometry, that's an if and only if its adjoint is an isometry. Or that's saying now that, or S dagger, or the adjoint of S, is equal to S inverse, and we can then refer to that or look at statement E up above. We also know from those statements that S and its adjoint preserve inner products. That's immediately true for S, but S and S adjoint are related, meaning they're both isometries. So if one's an isometry and it preserves inner products, and S dagger is an isometry, then it's going to preserve inner products. And that then says, let's just refer back to B and G, where G was just S dagger as an isometry. A was S as an isometry, and B simply showed us that we preserved inner products. Now we can just go back to the beginning and say, oh, A, S dagger is an isometry. Oh, then it must preserve inner products. Not only do they preserve inner products, but they also preserve orthonormality. It's a mouthful. But S and S dagger preserve orthonormality. So if you walk your way down to statement C and believe that, then all you have to do is jump down to G and realize that, oh, the adjoint of S is also an isometry. I can go back to ABC with that particular operator. Also, since S dagger S is the identity, this equality was statement C, and that's equal to S dagger which was statement F. Now we know, since they're equal to the same operator, S dagger, therefore S dagger S is equal to S dagger, and what does that tell us? So now in terms of a definition, what definition does this tell us is true about S? Or what are we doing here on the left side versus the right side? So now we have S dagger S, or if you think about it in matrices, just call them something different. You say AB is equal to BA, which means they commute. And if we have operators that commute, then we say that they are normal. So all isometries are normal. That's because S commutes with its adjoint S dagger. Those are now some properties of isometries and some of the consequences, or a way to summarize those. Now we can talk about a more specific description in the form of another theorem. This is theorem 43, which says description of isometries when our field is actually the complex numbers, the set of complex numbers. Now V is a complex inner product space, and S is a linear operator on that complex inner product space. If that's true, then the following statements are equivalent. Again, working on a complex inner product space. A, S is an isometry, and B, there is an orthonormal basis of our vector space, or our inner product space, which is complex, consisting of eigenvectors of that linear operator, again, which is an isometry, with all corresponding eigenvalues having an absolute value of 1. If we have an isometry, then we have an orthonormal basis on our complex inner product space that consists of eigenvectors of this isometry, and all of the eigenvalues of that isometry equal 1. We know none of them can equal 0, right? Because S is injective. It has an inverse. We've already actually shown this in one direction, essentially. The B implying A, we showed if we had all of our eigenvalues with an absolute value of 1, then that linear operator S is an isometry. It preserves norms. Remember, the norm of SV is equal to the norm of V. That's true when S's eigenvalues are all equal to 1. For the other direction, when A implies B, statement-wise, we can now assume A, which is assume S is an isometry. And what did we just comment about an isometry? All isometries are normal. So let's see if we can use that in this step. S is normal. Which means that S dagger S is equal to S dagger. But we learned something back when we were talking about spectral theorems about normal operators. The spectral theorem says there is a basis of orthonormal eigenvectors for that normal operator. Therefore, let's go ahead and just label the eigenvector to be lambda sub j. Let lambda sub j be the eigenvalue associated with the jth eigenvector. And we just now said from spectral theorem we have an orthonormal set of eigenvectors for that normal operator. If that's the case, then what's the absolute value of lambda sub j? That's just a number, a scalar, a real value, but if we look at scaling E sub j and taking the norm of lambda sub j E sub j, we haven't changed the value of that scalar, because what's the norm of E sub j? It's 1, because it's orthonormal. This was a orthonormal vector, or that now says that the norm of E1 is equal to 1, or I should say E sub j. But now that we have this scaled eigenvector, what's a scaled eigenvector in terms of the original operator? Or can we relate the scaled eigenvector when the scaling is an eigenvalue? Can we relate that to the operator itself? Think of the eigenvalue-eigenvector equation. Ax equal lambda x. In this case, it's S E sub j is equal to lambda sub j E sub j. We're just writing it in the other order. So that now this is equal to the norm of S E sub j. That's just the eigenvalue-eigenvector relationship inside the norm on either side of that equality. So S E sub j is equal to lambda sub j E sub j, so their norms are equal. But if S is an isometry, which we are saying it is since we're assuming statement A, what do we know about the norm of that isometry when it's applied to any vector? It preserves the norm. So now this is just the norm of E sub j. this was the definition of isometry. This is just eigenvalue, eigenvector equation. And we know that this guy tells us what we can put on the next side, or on the right-hand side of the norm of E sub j. That's just 1, and now we can compare the extremes on this equality. Now we know the norm of lambda sub j, or I'm sorry, the absolute value of lambda sub j is equal to 1. And that's true for all j. And that's what we were setting out to show in terms of this theorem. Or if we have an isometry on a complex inner product space, then we can find an orthonormal basis, and those are going to be, will be eigen, or we can find one that's the eigenvectors of S, and we know that the eigenvalues have absolute value of 1. Now we have these two pieces. We have a positive operator piece, an isometry piece. We're going to put those together to build a way of decomposing any linear operator that we have or that we're working with. And before we get there, let's just remind ourselves of where we have traveled. Let's now say we're motivating this polar decomposition of an operator T on a vector space V. And again, what we are doing really is we're combining these two concepts, a polar operator, a positive operator with a isometry to make a polar decomposition. We're combining positive operators and isometries as factors of T. Just like you can factor an integer maybe into its pieces, so that 4 can be factored into 2 times 2 times 1. Now we're factoring, maybe I shouldn't have done that. Maybe I'll leave off the 1 and just say 6, and that's 2 times 3. That's a way of factoring, but now in terms of complex numbers, we are actually going to factor this complex number into polar form, where it has a magnitude and an angle. Or recall the analogy between numbers and operators. For example, the first one, if we said, oh, let's just assume we have a generic complex number. Z is a complex number. What did we associate with that, or what was analogous to that in terms of what we've been discussing so far? That we simply said was this generic operator T. T is now this linear operator V. That was the start of our analogy process. Now if I said, what about the complex conjugate? Or now Z star. Now, if we have Z star, if we have the complex conjugate, and the complex number was T, what do we have now that's analogous to the number that's the conjugate of Z? That was our adjoint, wasn't it? So now that's T dagger, the adjoint. And remember this relationship by maybe our inner products. We're able to slide things around if we wanted to that way. What if we now had a real number? So that Z is equal to, or Z is real, or Z and its conjugate are the same. What does that imply with this analogy? My screen just sneezed. Wow, are you? If we now have Z being real, this number being real, then what do we have relative to the operator? It's now if we equated the A and B, that's really what we're saying, right? Line C is the equality between the complex number and its conjugate. What's that do to our maps? If we have T equal to T dagger, what's that tell us about T? It's self-adjoint, isn't it? So now we know that T is equal to T dagger, or now in this analogy, our maps are self-adjoint. D, what if we have a non-negative real? So that now Z is greater than or equal to 0. Now we're back to, or we're at the location where somebody was wanting to go in the last step, but now we're specializing row C to be even more specialized. Now we're saying that it's non-negative and T becomes positive. So now T is positive. And remember the disclaimer, that's really a little bit more than what it is. It's just the title has stuck, but it's really non-negative as an operator. We can have 0 eigenvalues. And finally, one that we maybe haven't really gone to yet, but we've talked about, what if this complex number has a magnitude of 1? What's that in terms of an operator analogous to? Now we're just rotating, aren't we? We're not expanding or contracting. And what did we say that was relative to these operators? That's those isometries. So now this is an isometry. What we want to do is pull out some of these pieces from this analogy on the left with numbers, with complex numbers, and use that way of decomposing a complex number and translate that into an operation or a decomposition of a operator. So now we're going to be inspired. So everybody needs to be inspired by this analogy. And what we want to now play off of is the fact that every complex number, or any complex number, can be expressed in polar form. Or now we can play with z. Z is a complex number, and I hope you believe that that statement is true. A complex number is equal to itself. Now, what can I do to itself and not change it? I can always scale it by 1. I can always hit a complex number with 1, and now I'm going to write 1 in a little bit more fancy way. I'm going to write 1 as a number over a number. That's 1. I haven't changed z at all. I haven't changed z in that form. But now I can start to shift that ratio around. So I'm going to slide the bottom underneath the left and keep the top on the right. Meaning, I now want to write that as z over its absolute value, or over its magnitude. And on the right is what I have left. I have to keep all my pieces. I can always multiply by 1, or I can always add 0, right? I'm not going to add anything. I'm just going to multiply by 1. But now let me rewrite z. What's z? Well, before I do that, let me put the left side in by itself. That's now some piece. And what is that piece? This complex number divided by its magnitude. That's like an angle, isn't it? That's like a direction. And the other piece is just the magnitude, but let me write that a little different way. I can say, oh, if I take the complex number and multiply it by its conjugate, and then take the square root, because z times z star is z squared, right? Let me just take the square root of that, so that I now have the square root of z conjugate z. Or this is now, if you wanted to think of it, this is on the unit circle. We've now simply normalized our complex number by its magnitude. And that's now going to give us a direction. And the right side piece is like the length of that vector. So we can turn this vector based on z divided by its magnitude or absolute value, and we can make that vector the correct length by scaling it by the square root of z star z. Now we simply go back and start using these appropriate lines in this analogy. We have E on the unit circle, which is what the left piece is. So we have an isometry piece. And we have, well, we don't have it quite here, but we have T dagger T square root. And we know what T dagger is. That's Z star. We have Z, which is T, and that's now going to allow us to find the unique positive square root of that operator. Or this expression now, which we were just playing with a complex number, this would suggest that any operator T on a inner product space V can be written as the following. T, we are now going to decompose our direction on the unit circle. That was an isometry. We'll just say that that's S. That's one piece of T. And the other piece is our magnitude or length piece, which is the positive square root, or the unique positive square root of t dagger t, where that was z star z, with S an isometry, where this piece is our direction piece, and this piece is our length piece. And that was all inspired by factoring or decomposing a complex number into its direction and length. And indeed, this is the case. We can actually decompose a linear operator into this polar decomposition. Indeed, this is the case. And it's written as a theorem, Theorem 45 in Chapter 7, and that's now the polar decomposition. And maybe this is very appropriate because I think we all may be having to wear our winter jackets tomorrow. The temperature might drop 10 degrees for a high. But polar decomposition. If we have t that's on a linear operator, then there exists an isometry we'll call it S, that's also a linear operator, such that t is now equal to that isometry times the unique positive square root of t dagger t. And now we want to show that. And this is kind of an involved process, but let's just try to keep track of what we have. If we've now decomposed this operator t into two parts, the left piece in this is an isometry. That's a direction piece. So we're going to have to show that S is an isometry, which means what does it do relative to, it's just dealing with direction, isn't it? And it's preserving norm. It's not changing any magnitude properties, but this square root of t dagger t is. That allows us to change the magnitude of this linear operator t. Let's see if we can step through some of these parts of showing that indeed we can decompose a linear operator into these two parts, one part being an isometry and the other part being the magnitude or the scaling piece. First, let's just start with t being a linear operator on V. And now let's pick any vector v in that vector space, capital V, and let's look at what happens when we start manipulating the norm squared of TV. V is generic, so this will be true for all V. Little v in our vector space, capital V. But you know how to rewrite TV squared, the norm of TV squared. The answer is yes. You know how to write that. How do we write that? That's the inner product of TV with itself. And what have we said? Oh, this is any operator T. So, what can we say about this? Well, let's play with the second slot. First slot, we haven't changed, but I can rewrite T as what? That's really vague, so I That was sort of rhetorical. But we could, if we had a complex number, if I conjugated it and I wanted the number back, I would conjugate it again, right? So I can dagger this a couple of times and preserve t, meaning in the second slot, I can now say I have t dagger daggered applied to v, and I haven't changed anything. But now, what if I want to slide that operator in the second slot into the first slot? What do I need to do? The easier way to view this is if I was starting with the correct inner product on the left, what would I have had to have started with in order to end up with what I have in that last equation? I would have to have been applying T dagger to TV because I've now daggered T dagger. And that's what I do to find the adjoint or to move an operator from the first slot to the second slot. Hopefully that's understandable. I now have T dagger TV, and I've now moved the operator from the second slot. And what do we know about any operator T dagger T? Well, to get to this point, this equality was just the adjoint definition. But now, what do I know about T dagger T as an operator? Do I know anything about T dagger T? It's positive, isn't it? This is positive. And we could go all the way back maybe to yesterday's lecture where we were saying any positive operator could be factored into these R dagger R. And now we're just saying, oh, our R dagger R is T dagger T, so this thing must be positive. So this is positive from, I think that was 35, theorem 35. But if we now have a positive operator, again, non-negative, what can we do with a positive number? If we just had a number and I gave you a positive number and I said, I can take a square root, can I? And we want to play with the positive square root. So let's now factor this, T dagger T, into its square root representation. Or we now have the inner product of the unique positive square root of T dagger T times the positive square root of T dagger T, V, V. This follows then from theorem 35, the previous one dealing with positive operators, and proposition 36, which is this unique square root of a positive operator. But now you can guess what I want to do. Let me kick that from the first slot back over to the second slot, or at least part of it, so that I now have, and the positive square root of T dagger T is self-adjoint, so I don't really need to put that adjoint symbol on it when I slide it from the first slot to the second slot, so that I now have the positive square root of T dagger T with V in the first slot. In the second slot, I have this positive square root of T dagger T with V. Again, that's the adjoint definition. And that's screaming at us, isn't it? That's telling us that that's just the norm of T dagger T applied to V. squared. Or if I could fit that all on one screen, I now have the left piece that I started with, TV, norm squared, equal to square root of t dagger t v norm squared. What does that tell me about the map t and the positive square root of t dagger t? So let me write that down here. I now have said, therefore, the norm of tv squared is equal to the norm of the positive square root of t dagger tv squared. What does that tell me about how the square root of t dagger t adjusts? Now you can't hear my hands going in and out with contracting and expanding, so I'll tell you that I'm talking with my hands now if you're listening. But now you're either contracting or expanding, but with these norms being the same, what have you done? Have you changed the contraction or expansion of this TV or this map T by the square root of t dagger t? No, whatever t does to the vector v, the square root of t dagger t does exactly the same. We've preserved the norm behavior. All of this scaling then, remember what we're trying to do. We're trying to decompose a map T into two parts, a direction piece and a scaling piece, and we've just demonstrated that the square root of t dagger t has not changed. It preserves the magnitude or the norm piece of t. The ability to contract and expand has now been preserved, and that's good because what does S do? S doesn't change that, does it? So the square root of t dagger t has the same effect on norms of t. And by the same effect on the norms, I'm really saying same scaling property. And that's good since S, which is an isometry in this decomposition, if it's an isometry, it can't manipulate the norm. It cannot adjust the norm. Therefore, the square root of t dagger t in this decomposition or in the factorization is really going to do the work that we need it to do. Is going to work the way it's supposed to work. But, it's always a but, isn't it? But now does this S do what we need it to do? Does S give us the directional piece? Is there an isometry? Let me say, is there such an isometry S? And now it gets a little busy. Now we want to, let me just try to give you the big picture as to what's going on. let's create, so we're really going to sort of build this isometry in two pieces, in stages. The reason is because this linear operator may not be surjective, meaning it may not cover all of the output vector space. And for that reason, let's create this isometry in two pieces. First, create an S sub 1 such that the range of the square root of t dagger t gets mapped into the range of t. So we want S1 to be rotating what's in the range of the square root of t dagger t into the range of t. The square root of t dagger t is just expanding and contracting, and that may not give us the direction that we need to produce the original map or the original operation. Once we have that, and again, that may not be covering the entire vector space, then we need to expand S1 to cover everything in that output vector space. We need to extend S1 to an isometry S. That's the big picture that we're wanting to work with. So let's now first define a map S1 that takes the range of the positive square root of t dagger t to the range of t. Let's just define that. Let's say that we can define such a map. Or we now have S1 operating on the positive square root of t dagger t v, and we're defining that to be the same as tv. This is now, in very simple terms, this is the input to S1, and we want the output of S1 to actually be what we create when we apply t, the original operator, to v. That's how we're defining S1. And the hope is that we can extend S1 to an isometry meeting our needs for S. We're wanting this isometry S. And the fact that we have S square root of t dagger t equaling t, that actually means that S square root of t dagger t v equals tv for all vectors in our vector space V. And what we have done in this definition of S1 is we've defined S1 to do just that. S1 has been defined to make this true. What we have to ask, though, but does this make this map that we've created, does this make S sub 1 a well-defined linear map? And the first piece that we want to check if it's well-defined is sort of this catch-all term, but to be well-defined linear map, first it needs to be unique, the map. So let's check uniqueness. Of the map. If it's not unique, then it's not going to work. So here to check the uniqueness, our statement is as follows. If we have two vectors v1 and v2, and they're related by if the positive square root of t dagger t v1 is the same as the positive square root of t dagger t applied to v sub 2, then if we are going to have uniqueness of our map, then we need tv1 to equal tv sub 2. If that's not true, we have no hope of creating an S1 to map S1 applied to the square root of t dagger tv1 into tv1. Or now we kind of have a proof within a proof. What happens when we have tv1 minus tv2? And t is a linear map, linear operator. So that now we can factor out those vectors, or factor the map, the linear operator. So we now have t applied to v1 minus v2. But what did we just show up above? We know that we can preserve the norm with this positive square root of t dagger t relative to t. And we now have this norm of tv, except now v is v1 minus v2. But we know this is true for any vector, so that now we can say that this is equal to the norm of the positive square root of t dagger t applied to v minus v sub 2, v sub 1 minus v sub 2. And now we can distribute that positive square root of t dagger t between v1 and v2. We can now say we have the positive square root of t dagger t v1 minus the positive square root of t dagger t applied to v sub 2. But that was our first assumption, wasn't it? We assumed that the positive square root of t dagger t v1 was the same as the positive square root of t dagger t v sub 2. So what's the norm of this last expression? Inside it's the 0 vector, so the norm of the 0 vector is z. Therefore, the right-hand side is 0. The left-hand side that we started with said tv1 minus tv2. Now we know that that has to be the 0 vector, or we've now shown that if we start with the positive square root of t dagger t v1 equaling the positive square root of t dagger t v2, we are assured that we will have tv1 equal to tv2, and that now preserves our uniqueness property. We'll have to pick up with that relative to what we're doing, but we've so far shown that we have the scaling piece. Now we have to worry about this isometry piece, and we're just getting started on showing that S is an isometry. We'll pick up at that point on Monday.